everyone, and welcome to another webinar in the Switch On Skills series of webinars. If this is your first one, then welcome, and if you've been before, welcome back. We're about halfway through the series up until Christmas, and then we'll probably do some more in the new year as well. I'm just going to briefly introduce myself and then start straight away. So hi, my name is Nathan Coos, and I'm an industrial lecturer at Swansea University. And as part of the webinar series today, I'm going to be talking to you about an introduction to renewable energy and the technologies that make up that sector. And that's going to make up the first half of the webinar, and the second half will be delivered by my colleague Mike Shakib on project finance to do with renewable energy projects. And feel free to scan the QR code to visit our website. I will be popping that up later on in the presentation as well, so don't worry if you've missed it this time. Okay, so the aim of this taster session, we're going to cover some of the main renewable energy sources and technologies that are relevant, particularly in the UK and more particular than that in Wales. And the majority of renewable energy sources, things like solar, wind, hydro, and geothermal energy, utilize energy from natural sources like the sun or the sea. In many cases, this energy is harnessed using ever-evolving technologies to generate useful power. So why? Why is this important? Why is this relevant, particularly now? We have an increasing demand for energy globally, and along with the diminishing stocks of fossil fuels, they're not going to last forever, and a desire to lessen environmental damage, particularly by reducing greenhouse gases emissions. This all points to the need for improved materials, technologies, and methods for generating renewable energy. So what do we mean by renewable energy? A renewable energy source means energy that is sustainable. In most cases, it's something that's not going to run out, or at least not anytime soon. So we can consider it as endless, like the wind or the sun. You may have heard the term alternative energy, and this is again referring to renewable energy sources. It means sources of energy that are alternative to what we have traditionally burnt to produce energy, like coal, oil, or gas. And these are considered to be non-sustainable and therefore non-renewable. So energy conversion from renewables. Electrical energy can be generated in many ways. Mechanically, either directly driven from things like hydro, wind, or wave and tidal technologies. It can also be directly generated by a fuel cell or things like a battery, which is chemical to electrical energy. We have PV or photovoltaic energy directly from solar to electric. And we also have something called the Seebeck effect, which is a phenomenon where there's a temperature difference between two dissimilar electrical conductors or semiconductors. This produces a voltage difference between the two substances. So it allows us to convert thermal energy from the sun to electric energy. Something not mentioned on this list is nuclear generated electricity. It's not strictly classed as renewable, but it is low carbon, as it's not strictly renewable because it does use radioactive substance to generate the energy, and also it does generate radioactive waste, which has to be stored safely. However, it is low carbon, which means its generation emits low levels or almost no carbon dioxide, just like renewable energy sources, and it will probably play a big part in the UK's ability to achieve net zero status in the future. So solar energy, what do we mean by solar energy. So sunlight is one of the most one of our planet's most abundant and available energy resources. This is probably one of the when you say renewable energy, this is probably what most people think of straight away is solar panels. We see them popping up on houses regularly, and it's I don't know, I guess a fairly obvious one where the sunlight we know we're having obtaining lots of sunlight every day, and we're able to harness that energy and most of the time convert it into electricity. So this is an interesting sentence. You may have come across this before, but the amount of solar energy that reaches the Earth's surface in 1 hour is more than the planet's total energy requirements for a whole year, which is absolutely insane. So if we can harness just some of that, then we'll be sort of well on the way to more sustainable energy. Of course, the amount of solar energy we can use varies according to the time of day, the season of the year, as well as geographical location. So some areas will receive more sunlight than others. And in the UK, as I mentioned, solar energy is an increasingly popular way to supplement your energy use, both domestically and industrially as well. Just going to play this short video, and you may recognize the voice because it's me. Almost all of the Earth's energy input comes from the sun. The sun is therefore vital to life on Earth, but not all of the sunlight that strikes the top of the atmosphere is converted into energy at the surface of the Earth. Much of its light is reflected. In fact, the Earth's albedo, which is the ability of a surface to reflect sunlight or solar radiation, reflects back around 34%. Snow and ice have high albedo. Most of the sunlight hitting surfaces covered with snow and ice bounces back. In contrast, dark, earthy surfaces have a low albedo. Therefore, they absorb more sunlight. The amount of energy that reaches the Earth provides a useful understanding of the energy for the Earth as a system. This energy goes towards weather, keeping the temperature of the Earth at a suitable level for life, and powers the entire biosphere. Additionally, this solar energy can be harnessed to be used as a primary energy source, either with solar thermal power plants, solar panels, or photovoltaic cells. Okay, so as the video mentioned, solar energy can be seen as inexhaustible and is classed as a renewable energy obtained from the electromagnetic radiation from the sun. And it does this, generates electricity and heat in a manner which is sustainable and free. A little fun fact for you there, well, not a fun fact really, it's just a note. Solar energy does not produce air pollution or greenhouse gases. Once the technology is already made, I should say. Obviously, during the manufacturing process, there is carbon dioxide emissions associated with that. But the main environmental impact of solar energy is the use of the land and potential loss of habitat in the case of large solar energy farms. There are three main types of solar energy. PV, photovoltaic solar energy, which is used to produce electricity directly from the sunlight to convert into electricity. Next, we have solar thermal energy, which is a way of using the heat from the sun to heat water or air. And then this can be then utilized in buildings. And we can also utilize the solar energy passively, which directly takes advantage of sunlight. So for example, a sun-facing room will heat itself essentially when the sun is shining. So that's a way of passively using solar energy. And emerging technologies are starting to be sort of introduced now, and these are a combination of the first two. So they are thermoelectric systems. Some obvious advantages which we've already touched on for solar energy include the fact that it's renewable, abundant, there's no polluting emissions into the atmosphere. We have it's becoming an increasingly competitive energy source, and it also reduces our reliance on the electricity grid as well. There's subsidies for self-supply, and it will be a key measure against climate change. However, some disadvantages, particularly in Wales, the sunlight can be very unreliable, intermittent, and solar cells are actually quite relatively inefficient. So that's something that needs to be considered when installing solar PV. We also have a high initial investment in terms of the solar cells or the technology used to capture the solar energy, and the location of homes and buildings may not be the sort of the best for solar energy. So moving on to another major player in this, particularly in this area, wind energy. What do we mean when we say wind energy and wind power? These both describe the process by which the wind is used to generate mechanical power or electricity. So this was used traditionally as grinding for grinding grain or pumping water, where mechanical power can be used for this. Or more recently, a generator can convert this mechanical power into electricity using wind turbines. Wind is actually a form of solar energy caused by a combination of these three events. So the sun unevenly heating the atmosphere, irregularities of the Earth's surface, and the rotation of the Earth. So we do expect wind to be around for some time as well. Meaning that it's a plentiful source of clean energy. Wind farms are an increasingly familiar sight in the UK, with wind power making an ever-increasing contribution to our energy production. To harness electricity from wind power, wind energy turbines are used, and then these then can either be used in situ or feed electricity into the national grid. So domestic systems are available, but not every property is suitable for a domestic wind turbine. Again, I'm going to play a short video, and this is the last video of my bit anyway, and then I'll go through some further slides following this. The video is mostly on is aimed at offshore wind, but it also describes general wind turbines suitable for onshore as well.
Today, we will learn more about the exciting world of offshore wind energy. Ever wonder how those giant wind turbines out at sea work? Stick around, and we'll explain everything you need to know about this powerful and clean energy source. Electricity from offshore wind is generated by wind turbines located in bodies of water, usually oceans or large lakes. But why put them in water, you ask? Let's break it down. First, let's consider the benefits. 1. Stronger and more consistent winds. Winds over the ocean are typically stronger and more consistent than on land. This means offshore turbines can generate more electricity. 2. Less visual and noise impact. Offshore turbines are far from residential areas, reducing noise and visual impact on communities. And 3. Space efficiency. Large wind farms can be built without the same land use concerns as onshore wind farms or solar panels. This is particularly beneficial for densely populated coastal regions. So, how does this work? Wind turbines convert kinetic energy from the moving wind into rotational energy and then into electricity. Here's a closer look at the process. Blades catch the wind. The wind turns the blades of the turbine. These blades can be over 80 meters long and are designed using advanced aerodynamic principles to maximize efficiency. Rotor spins the shaft. The rotating blades turn a low-speed shaft connected to a gearbox. Gearbox increases speed. The The gearbox increases the rotational speed from about 30 to 60 rotations per minute to around 1000 to 1800 rotations per minute, which is suitable for generating electricity. Generator produces electricity. The high-speed shaft drives the generator. Inside the generator, the mechanical rotation is converted into electrical energy through electromagnetic induction, and finally, electricity transmitted to shore. The electricity is then transmitted via underwater cables to the shore and into the power grid. These cables are typically high voltage alternative current or high voltage direct current lines, depending on the distance to the shore. Now, let's consider some technical details of key components. 1. Blades. Made from lightweight composite materials like fiberglass or carbon fiber to withstand harsh marine conditions. Their shape and angle are optimized for capturing maximum wind energy. 2. Nacelle. This is the housing at top of the turbine tower, containing the gearbox, generator, and control systems. It's designed to protect these components from the salty and humid offshore environment. 3. The tower, usually made of steel and can be over 100 meters tall. The height allows the blades to reach higher and more consistent wind speeds. And 4. The foundation. Depending on the water depth, foundations can be monopile, jacket, or floating. Monopiles are used in shallow waters, jackets in deep waters, and floating foundations for the deepest locations. Let us think about environmental impact. Offshore wind farms have a much lower carbon footprint compared to fossil fuels. They don't emit greenhouse gases or air pollutants, helping to combat climate change. However, they must be carefully located to minimize impacts on marine life and ecosystems. Detailed environmental impact assessments are conducted to understand potential effects on marine mammals, fish, and birds.
Okay, so there's more to that video. I just wanted to show that snippet for this presentation. It is available on our YouTube page if you wanted to watch the whole video. So there are two main types of wind turbines. The first one you're probably more familiar with. It is a three-blade system, and these are called a horizontal axis wind turbine. These operate upwind, with the turbine pivoting at the top of the tower so the blades face into the wind. But we can also have vertical axis wind turbines, which are omnidirectional, meaning they don't need to be adjusted to point into the wind to operate. And as well, they can be placed on top of existing structures, so buildings and things like that. In terms of applications, this is an interesting schematic showing different sizes and powers of various wind turbines. Land-based wind turbines range in size from around about 100 kilowatts to as large as several megawatts. The larger wind turbines are more cost-effective and are grouped together into wind plants, which provide bulk power to the electrical grid. If you look at the schematic, you can see that by 2035, we're expected to have much larger wind turbines, both onshore and offshore, doubling the capacity to around 5.5 megawatts compared to 2.5 megawatts, for example, for onshore. And then the offshore wind turbines tend to be absolutely massive. There's more space to work with and utilize the stronger winds offshore. And these can generate, predicted to generate up to 17 megawatts of power per turbine in 2035. And there's some sort of statues of structures around the world there for reference, and you can see they're already towering over the Statue of Liberty, and these larger offshore wind turbines are even approaching the height of the Eiffel Tower. So yeah, these things are absolutely huge, but they will be able to generate much of our power in years to come. In terms of other applications, you can get smaller single wind turbines below 100 kilowatts. These are typically used for residential, agricultural, and small industrial applications. You see that I've been watching a lot of kids' telly recently, my son, and the Teletubbies have got one. You may recognize that animation in the bottom there. But realistically, they'll look a bit more like the other image there, the top image. Unfortunately, no animations with that one. So these can be used in hybrid energy systems along with other distributed energy resources, such as microgrids powered by diesel generators, batteries, and photovoltaics. So a combination of these will be typically used in remote and off-grid locations. Some obvious advantages of wind energy that it can be made to be cost effective, clean, sustainable fuel source, and wind turbines can be utilized on existing farms. Some disadvantages, it must still compete with conventional generation sources on a cost basis. Wind resource development might not actually be the most profitable use of the land, so that is something that needs to be considered before going ahead. Often these are located in remote locations far away from the cities where the electricity is needed. And as the video mentioned, it might cause noise, aesthetic pollution, and harm the wildlife. So to break that down even further, in terms of environmental impact for onshore wind turbines, we have disruption of the habitat and land use, disturbing local ecosystems potentially. We've got wildlife impact, particularly on threats to bats and birds. As you can see there from that image, noise and visual impact if residential areas are nearby. Carbon footprint, so even though they don't give off carbon dioxide, if you emit carbon dioxide when they're running, it's often generated during manufacture. So that needs to be considered, and impacts to the soil and soil and water, changing the flow of the water naturally and the erosion of the soil as well. So all these things need to be considered before installing a wind turbine. Offshore, we have very similar impacts. We have marine impacts of the marine ecosystems, especially during construction. Obviously, bird collision risks, unfortunately, particularly migratory species. They actually create artificial reefs, so this often will change of course, will change the biodiversity in the area, but it does increase the biodiversity. Visual impact, the coastal views obviously are affected by large wind turbines, and the operational carbon emissions. So these are often higher than other renewables, mostly because they're remote and in the sea. So they take the higher emissions to maintain and inspect the turbines. Moving swiftly on to hydro energy. This is one of the most commercially developed renewable energy resource around the world. And to put simply, by building a dam or barrier, a large reservoir can be used to create a controlled flow of water that will drive a turbine, again, similar like wind energy, to generate electricity. And it can be more viable in the same way as wind energy can be more viable in some places compared to solar and other sources of energy. This is a schematic of the basic process, and the way that it works. The dam will store lots of water behind it in the reservoir on the right-hand side. Near the bottom of the dam wall, there is the water intake. Gravity causes it to fall through what we call the penstock, looks like a large slide. And at the end of the penstock, there is a turbine propeller, which is turned by the moving water. And similarly with a wind turbine, then that mechanical energy generates the electricity, and then you can be distributed then to where it's needed. Advantages, it's a low emission renewable energy source, reliable and safer than some other sources of energy. Disadvantages, we have the obvious environmental consequences of creating reservoirs if they're man-made, expensive to build, potential of drought, and limited reserves. Tidal energy, this is another form of hydro energy that uses twice daily tidal currents to drive turbine generators. So although tidal flow, unlike some other hydro energy sources, isn't constant, it is highly predictable, so can compensate for the periods when the tide is low. At Swansea Bay, we have the Blue Eden Tidal Lagoon in some sort of pipeline set for development, and that's set to feature underwater turbines generating 320 megawatts of renewable energy. And here we have a basic schematic of the process. There's different types of tidal energy. This one uses the tidal barrage, where the flow of the tide will pass through the turbine, generating electricity. We can also see similar technologies being used in tidal lagoons as well. Advantages, it's a compact renewable energy source with zero emissions, more reliable than other types of hydro energy. Disadvantages, of course, environmental consequences, again, nearby biodiversity, expensive to build and can form silt behind the barrage, and very few suitable sites potentially for constructing these barrages. This is a whole topic in itself, and it will in fact be presented as part of our webinar series in a couple of weeks' time. Hydrogen as a fuel source. I wanted to mention it today because it does link very well with renewable energy technologies. It's an energy carrier and can be, hydrogen is an energy carrier and can be produced from a wide variety of sources and is used to refine petroleum, treat metals, and produce fertilizer and processing foods. It can also be produced from renewables in a number of ways. Typically, the process uses renewable electricity to split water into hydrogen and oxygen in an electrolyzer. Hydrogen could be stored on sunny days when the rate of renewable energy, electricity, and in turn hydrogen production exceeds hydrogen demand. And this stored hydrogen can be converted back to electricity with a hydrogen fuel cell to produce a continuous renewable electricity supply, even during periods when the rate of renewable electricity production cannot meet demand. So these fuel cells have now been sort of installed and used in transportation, cars and lorries, and even I think trains are in the pipeline as well. So the reason why I wanted to mention it was because there's many different ways hydrogen can be produced. One of them is green hydrogen. This is a method of generating hydrogen which uses renewable electricity to make hydrogen from electrolysis, with oxygen being the only byproduct, and then with surplus hydrogen stored underground before being used for something called direct reduced iron, DRI production, with water being the only byproduct. And finally, with DRI and scrap used to make steel via the electric arc steelmaking process, powered by yet more renewable electricity. So you can see how all this links back to renewable electricity. It may look ideal, but the technology is currently very expensive. So nothing really is commercially going forward with this at the moment, but research and development in these areas is ongoing. Just some brief comparisons before I finish. So wind and hydropower are very consistent. Wind turbines may have a higher maintenance cost because the turbines are larger and break down more easily. Solar, whereas it's a cheap energy source, may be less reliable or less consistent than hydroelectric power. Hydrogen fuel cells are being introduced. However, emissions generated during extraction vary between methods, and green hydrogen is, like I said, is expensive at the moment. Biofuels, which we haven't mentioned in the presentation, but these are generally worse for the environment because you still have to cut down the trees or plants that will need to be burnt for the fuel. But with solar, wind, or hydropower, generally these resources are plentiful and do not emit CO2. Last two slides before I finish. So wind and solar power in terms of future trends in Wales, these are expected to make up a rapidly increasing share of the energy mix in order to replace fossil fuels. In order to meet the UK and Welsh renewable energy and decarbonisation targets. The share of these different technologies is unknown at the moment, but it will become more clear as these developments get approved. And it's expected that the share of onshore wind and solar will make up a lot of decentralized generation, while offshore wind has the potential to provide large-scale centralized generation capacity. And lastly, wave and tidal power. These will probably also play a large role in Wales's future energy mix, and several demonstration projects are in development at Anglesey and Pembrokeshire, and these, if deployed at scale, could demonstrate cost competitiveness with other generation sources. And as mentioned, tidal lagoons are also being explored, but they have concerns over the cost to UK consumers. Thanks very much for listening. I'll now pass over to my colleague, Mike Shakib, who will discuss project finance. Thank you.
Right, I'm going to make sure that, Chris, can I have a check? Is everything working here? Can I carry on? Nathan?
Yeah, all looks good.
All good, brilliant. Okay, right then, project finance. Why are we here today then? This is the concept of why we're here today and why I want to talk about this. So Nathan's talked about renewable energy assets, a whole range of them. So we're here today because we want to build a renewable energy generator. So I knowing about this, so I talking about it. How do we get these things built in real life? Okay, this could be a wind turbine, it could be a solar array, hydro, anything. It doesn't really matter what it is, right? It doesn't matter. Crucially, what do we know already? We know that these things cost money. Some of them cost a lot of money, some of them cost a lot of money, right? So we know that we need a lot of money, and we also know that they probably cost more than what we have in the bank. Okay, we may have zero money in the bank. We know that we may not have the technical knowledge to build these systems, and that's often the case. Not everyone's got the technical knowledge to build a renewable energy generator, but we can still do it, and I'll show you how. We certainly don't want to lose money on these projects and hope, well, we definitely want to make money, okay, when we're building something like this, right? That's the bottom line. We want to make money on it. Knowing all this, do we still want to build a renewable energy generator? Yes, we do. How are we going to do it? We're going to use something called project finance. I'm just going to read you from the screen. Project finance is the funding of long-term infrastructure, industrial projects and public services using non-recourse or limited recourse financial structure. The debt and equity used to finance the projects are paid back from the cash flow generated from the project. Project financing is a loan structure that relies primarily on the project cash flow for repayment, with the project's assets, rights and interests held as secondary collateral. I know that went in one year and out the other. It doesn't really mean anything to us in words, okay? So the whole point of this course is to actually try and put it into some sort of practice. So this is a perfectly adequate explanation of project finance, but it definitely leaves the door open to further questions and clarification. So let's take it one step at a time. Let's say we want to build wind or solar project. We have to have an idea. That idea can come through a group of people, one person, and we'll talk about that a little bit more in a second. These are physical assets that are going to sit on land for many, many, many years, 25, 30 years, 35 years. There needs to be a willing landowner involved in this negotiation. A council needs to be involved, a local council who is going to give you planning permission. They need to be involved. The connection to the power grid is pivotal. They need to be involved. There needs to be people involved who have technical expertise, people who have done this before, people who can run and build and run an asset such as this. We need money, okay? We need money to get this project built. So we need some kind of financing, all right? There's many, many ways in which we can get this done. So just to build up a picture, here we are in South Wales, okay? We say between Ammanford, Pontardawe and Pontarddulais, we want to put ourselves a nice wind turbine somewhere. There's plenty of wind turbines around there, so they would have all gone through this process. So we approach the farmer. We have a discussion and say, I want to build a wind turbine there. Is that all right? And the landowner goes, yeah, no problem. You can build a wind turbine on my land. I'm not really doing much with it, in that area at the moment. It's going to cost you, obviously. You're going to need to take them down after a certain number of years. You need to make sure that my neighbours don't complain. In which case, we think at that point, well, we're probably going to need some planning permission. So I want to build this wind generator. The farmer said it's okay. Things are now starting to get a bit real. Does it actually work? Does it work on a technical level? And does it work on a financial level? And I've highlighted here the word we. Can we do this? Because who are we? In this picture, who are we? Okay, who's doing this? Well, usually when you set up, usually when you want to go and develop a project like this, you need to set up some kind of company. And in the world of this, in the realms of this particular world, usually that's called a special purpose vehicle. So a special purpose vehicle is just a generic legal term for a company. And for argument's sake, we'll go through it in more detail in the course. Let's call it a private limited company, a public limited company. What else have I got there? Limited liability partnership, a company with limited after their name. What does this company do? Well, it owns the company. It is the company. So it owns shares. Directors of the company will make decisions. Assets will be purchased through that company and held within that company. Loans will be taken out in the name of that company. All of the income, all of the revenue, and all of the expenses and all of the liabilities belong to that company. Crucially, the special purpose vehicle or the company is ring-fenced from other assets and liabilities. That's the definition of this non-recourse or limited recourse liability. That's important as well. We'll talk more about that during the course. So can we do it? The first thing we need to do, the SPV or the company needs to do, is find out what are the showstoppers. They call it this in the business. They call them showstoppers. Okay. So we need to technically do this. Can our project be constructed within our proposed schedule and budget? What is our schedule? What is our budget? Okay. Once it's completed, will it be able to operate at planned capacity or will it not? There's plenty of reasons why it won't. Okay. And we talk about those in the course. So at this point, you're thinking to yourself, well, I don't really know the answers to these questions. Do you know the answer to these questions? Are you looking over to your colleague and he's like, no, I may know some, but not all of them. I think we need a bit of help. So decide, you need help. What are you going to build? You're going to build a turbine, a generator, a hydro turbine, a solar farm, whatever. Okay, and what is it that you need? How much energy will that produce usually in a year? Is that going to depend on its size? Yes. Well, if we go bigger, then maybe the council won't like us. They won't give us plan permission. Okay, so we need to balance all that out. Can we get our turbine up onto that mountain that I just showed you? We're going to have to build a road. Okay. Will the council object to this turbine based on anything else? Is there an ancient monument on site? Is there a protected habitat? Is there an airport nearby? I've been through all this with the council, and these are all the things which have been showstoppers. Okay. Can I get my energy to grid? That's a big one. Will the energy I produce be able to get on the national grid? It could be expensive. The answer is normally yes, but they'll charge you for it. Okay. If I can't get onto the grid, is there someone nearby? Is there a very large off-taker, an industrial estate, a private company, or I can sell my electricity to? These are all the questions that you need to find out before we go any further. Who finds this out? Well, the initial idea is probably you, as in the special purpose vehicle and your colleagues around you. On the technical level, how can you find out whether this works? Well, there are, okay, for instance, I've said resource scoping. So there are free tools which you can use on the internet, and they're very, very good. And we'll go through them later. Then there's costly software which you can use, and you can also employ consultants. And to be honest with you, you will probably end up doing a bit of everything. You'll do an initial feasibility study yourself, and eventually you get a consultant in who will provide a package for you, which will contain things like how much electricity can I produce in a year and all that sort of thing. Grid connection, you can talk, anybody can make a grid connection offer. You can talk to the DNO, and you can get a good connection off. Anybody can do it. You can ask your consultant to do it as well. Planning permission. This costs money, and I tell you what, it costs a bit more than what you think as well. It costs a lot of money to do planning permission, okay? There are companies who will do this, and we will not cover any more about planning permission in this course. Nothing. It's the last, well, it's not the last. It's almost the last time I mention it. Then we need to do financial modeling, because we need to find out if this works. And it costs money to actually do a financial model. However, that is why we are here today, because this course is aimed at the sort of introductory level of how to do a project finance model. So that's exactly what we're going to do there, point 3. There are companies that will do this, and you probably will want to approach those companies in the end, but we're going to learn how to do this on a basic level. So we're going to learn about technical feasibility, resource scoping. We're not really going to talk more about grid connection, and financial modeling. That's what we're here to do. So assuming we have planning permission, and all the other technical aspects are catered for. Okay, we know this project works, all right, and technically. We need to build it. How are we going to do that? We haven't got any money. So we need to borrow money to build this electricity. Sorry, we need to borrow money to build this asset, which will generate us electricity. And electricity isn't for free. The reason why you're generating electricity is because you want to use that to create a revenue stream. All right, so you want to sell the electricity to get some money in. We then use that revenue to operate and maintain the asset, pay tax on any profits we got if we need to, pay back loans and interest, okay? And finally, if there's any money left over after doing all of that, you can pay back the people who have lent you money in the beginning, your stakeholders, your sponsors, all right? So you see an opportunity, you want to build a renewable energy asset, you've got no money, you've never generated any money, you've got no credit history, you've got no employees, maybe you've got some employees, you've never operated before, and you've got no guarantees that you'll ever be able to pay back a loan. In short, doesn't seem like a good start, does it? But this is where project finance comes in, because project finance is about it's about financing long-term infrastructure which relies on project cash flow. Okay, rather than reputation of a company, it relies on cash flow, and we'll go through that in more detail. It's a perfectly common way of financing all areas of large infrastructure. You can use this to look at building a road, an airport, power plant, whatever. It doesn't matter. Right? This is the holy grail. This slide I'm showing you now is the essence of project financing. Right? In the middle, we have the SPV, special purpose vehicle. Right? We have to build this. We have to build this asset. It's going to cost money. That money is called capital expenditure. It's called CapEx. We shorten it to CapEx. Once the asset is built, it starts to generate a revenue. So we see here we've got cash flowing out of the business here, cash flowing into the business. Also, there's something else here. We need to keep this thing operating. In order to keep this thing operating, it needs annual maintenance. So it needs ongoing maintenance, okay? So that represents cash flowing out of the business. So we got revenue coming in through our sales of electricity. That then goes to serve the operating expenses. So how do we get our capital expenditure? Because our yield, okay, our revenue here doesn't start until the actual asset is being built. So in order to raise enough money, to raise the £1 million, the £2 million, the £3 million to actually build this, we need two things. Well, we could have three things. We could have a number of things. But basically, we are focusing on debt and equity. Debt is when we go to a bank and we want to loan money from that bank, and we loan that money on the basis that we pay back the principal and some interest. So the bank will lend us money. That's positive money flowing into the business, and that's cash flow out to the business through capital expenditure. Equity is when we have sponsors, shareholders, and we convince them that the project is good enough. They actually put money into the project in terms of funding, so that money will flow in. So it's a positive arrow flowing into the business, and that money will then go to actually funding the project, the capital expenditure. So that's the very basics of it. Let's talk a little bit about revenue. So revenue is basically, we produce the electricity, we have a PPA, a power purchase agreement contract with a buyer, such as Octopus, who are some of the other big players in the field. I can't think of them off the top of my head now. Ecotricity, those people. They will buy the electricity from you at a certain rate, and basically that's your business model. You produce electricity and you sell it to a company that's willing to buy it off you, and it's usually one of those sort of clean renewable energy companies that will buy it off you. So that's your revenue stream. So debt, we'll go through it in more detail in the course. You will pay it back in the future with interest. You need to have a clear visibility of the profitability of the company. You need to be able to pay back your loan, basically. And if you can't, the bank may step in and retain full ownership. So there's always risk involved with borrowing money. Things that the bank wants to know before lending you money, they will do a due diligence risk assessment. They'll arrange fees. They'll charge you for the privilege of borrowing money. Okay, and there's other things as well which we'll talk about. So yeah, there's loan length and interest rates and all that sort of stuff, which probably all people already know about. Okay, you borrow money for a certain amount of time, you pay back a certain interest rate, and you'll have to pay fees for the privilege. Equity is a little bit more interesting. So if you want to finance this project based on having equity, well, what that means is you take capital from outside investors, okay, in exchange for some kind of ownership in your company. So typically investors will receive dividends every year. So you buy shares in a company and you expect to receive dividends if the company does well. That's the risk. So you end up having to when you do this, you give up some sort of ownership of your company in terms of decision making as well, because you usually have to have like an AGM meeting and stuff like that. So you give up some level of ownership with your company when you have equity. And it may be quite an extensive process as well, getting people to actually want to invest in your company. In terms of the ratio between debt and equity, usually we're looking at about 30%. So 70% debt, 30% equity. So assessing the project's viability. So whether, in both cases, whether you're using debt or equity to fund your project, both of them are going to want to know. They're going to want to know it works technically. They're going to want to know that it works financially. Okay, they want to know the credit worthiness of this project. They want to know you've done a due diligence process. They want to understand that you can actually construct this project within a certain time period. They want to know the schedule. They want to know the budget. They want to know everything about the project. You cannot hide anything from them. They need to know everything. The question is, how do we start doing this? So we already know that building a project has risks. And I found this definition of risk on the internet, and it says a good way to mitigate risks in a project is to understand them and allocate them to the best placed people to handle them. And that's exactly what project finance is about, okay? We want to attract money from investors and the bank. We want to do so in the form of loans and equity. Funders need some kind of guarantee that you're serious and capable. And to do this, and to de-risk the project, we set up a series of contracts with people who understand the risks the best. So back to this diagram, okay? The SPV, special purpose vehicle, wants to build this asset. They don't know how to build it. So they go out to an EPC contractor, okay, an engineering procurement contractor here, which does know how to build the project. And they go through a lengthy negotiation of everything, budget, time constraints, everything. And they will be the people who build your project, and they will be reputable, hopefully. It's better if they're reputable. If they're not, give them a chance, maybe. If they're not, you may wish to have an owner's engineer. And now an owner's engineer will sit in between you, the EPC contractor, and they will kind of like do checks on the EPC contractor. They make sure that the contractor is doing things right. There'll be a second check, and they should work in harmony with each other. They should meet each other. They should be friendly and have a good working relationship with each other. And you should have a good working relationship with your EPC contractor, your owner's engineer, and other people, because the EPC contractor may not take on all the work. For instance, if you want land work done, groundworks done, okay, you as a decision maker, okay, you're the SPV, you're basically the boss of this project. You may decide that you don't want the EPC contractor may be from Cardiff or Bristol, okay, and they may bring all their people in from there, and you may decide that you prefer to use a local contractor to do your groundworks, for example, all right. So that's just an example of the interplay between there. So you'll be speaking to your contractor and your owner's engineer and your contractors as well on a daily basis, probably, or weekly basis. Your power purchase agreement is a contract. You sign a contract with a company, an electricity supplier, and that's it. That's your contract. And the bank or the equity people will be happy that you've signed a contract to say, I will sell the electricity I produce from this site for 8 pence a kilowatt, 7 pence a kilowatt, whatever it is. You will also have a contract with operation and maintenance company who will be responsible for maintaining your project. And the SPV will constantly be renewing these, they'll constantly be working with these, and they'll constantly be working with these over the course of the project. All right? Some other contracts which you have to take into account. We've got local planning, so the bank will obviously want to see that you've done your planning permission. We've got things like curtailment and BATs and blah, 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 blah. Landowner, there needs to be an agreement with the landowner. There needs to be a lease ahead of terms. There needs to be rights of way. There needs to be all sorts of things. Electricity off-taker, we need to have a grid connection in place. We need to have a signed letter from National Grid to say that they're happy with this, and all the rest of it. Who else have I got here? So I've said financing, typically 20 to 30% financing. That could be from equity financing, sponsor, or something I haven't mentioned yet. That could be from grants and community ownership as well. So that could be part of your funding. And you'll typically pay, dividends each year to your financiers. And then we got about 70 to 80% bank loan agreement. So what about timing then? So project finance is a lot about timing. How long have I got? 8 minutes. So let's talk about timelines. So say you can develop your project within a year. It may take longer, okay? That development phase requires money to do so. It may require more money than what you think. You could be talking 40, 50 grand development costs, if not more, something like that. So that's got to be paid for. Construction. The construction phase is usually, of course, that was a big, say you're spending £1 million, that's a big negative to your bank account. Only in the operation phase, which can be about 25 years, do you actually start making money. And this is probably one of my favorite diagrams I've ever produced. I quite like it. This gives you a project timeline, all right? A sort of block diagram to show what's happening along the length of the project. So here's project timeline. We've got project steps here. The development phase will say that it takes a year, and it's a very high risk time of the project. And these are not in order. So during the development phase of a project, you'll be doing your technical feasibility study. You'll be looking for your planning. You'll be doing your grid connection, your PPA. You'll be discussing with lenders, grant holders and stuff like that. And you'll be doing this all at the same time, basically. It's not in order like this. Part of the development phase is you will be doing a financial viability model. Okay. Now, like I said back here, usually during the development phase, the money in which you spend is going to come from equity, funding, or grants, or something like that. Okay. The bank doesn't start lending you money until the risk gets a little bit lower. Okay. Till all these contracts are in place, that's when the bank says, okay, I can start lending you money for construction, basically. So equity and grant funding up until the construction period. And then after the construction period is over, we have an operation and maintenance contract. Dividends then get paid out to the shareholders, and interest and principal get paid out to the bank. We still haven't discussed yet what project financing is. We still haven't looked at a spreadsheet. Here we go. Now we have to understand who are the key players in our project. The key players are us, the SPV, equity investors, that's 2, and debt financiers and contractors as well. Okay, so what do these people want to know? What is it that the bank needs to know? What is it that the shareholders need to know in order to want to invest in this project? They need to know if it works, and what does that mean? Okay, so now we start to get into things like working out the EBITDA, okay, which is the earnings before interest, taxes, depreciation, and amortization. They want to know the project IRR, which is the internal rate of return. Are these things starting to feel a bit familiar for you now? Now people have done this in the past may start to think, oh yeah, I know what I'm talking about now. They need to know the net present value. The bank needs to know what is our cash flow available for debt service. What is our debt service cover ratio? These things are just absolute alien to most people. What does all this stuff mean, you know? But don't worry, at the end of this project, you will know. What do our investors want to know? They want to know what the equity IRR is of this project. If we put these back on the diagram, this is basically what I've said here, but back on the diagram, all right? How do we work out if this project works? Well, we need to work out the project IRR, the pre-tax cash flow, the EBITDA, the net present value. Bank wants to know its CFADs and its DSCR, and the investment wants to know the equity returns. How do we do that? Now, we also have got things like tax and capital allowance and stuff like that, but I'm running out of time, so I'm going to be really quick now. How do we find out all this? We use cash flow analysis. We use project finance, okay? So we will be eventually creating a spreadsheet. This is a schematic of a spreadsheet that looks a bit like this. Here we have a timeline across the top. Year 0 or period 1 is construction. That's when we pay for our CapEx. We pay for a project. Year 0, we have no revenue and we have no operating expenses. From year 1 or period 1 to period 19, we start producing revenue. So therefore, we have to start paying operating expenses as well. From that, we can work out our project IRR, our net present value. We look at tax and depreciation. We look at debt. We look at debt sculpting. So we look at different ways of paying back interest and principal. We work out cash flow available for debt funding. We work out our equity IRR. And that's called the cash flow waterfall, all right? And we'll go through this in a lot more detail. You take your revenue, you take away your expenses, then you'll be able to calculate your EBITDA. This is important because it shows you who needs to be paid first. So the taxman gets paid first, then the bank gets paid, and then we get distributions to equity. So how do you work out all of that? I'm conscious I'm rushing a little bit, but I am running out of time. We are going to produce a model, a project finance model. So you will be, this is on Excel, and you'll produce this. You'll understand what all these true and false things mean. This is our timeline at the top. This is literally our timeline of our project, our construction phase, our operation phase. These are our important outputs, which we will get to. And you will construct this yourself. Now I'm going to give you this, yeah, but I wouldn't use it. It's of no use to you unless you actually construct it yourself and understand it, because no one's actually going to look at this. You can't use this model I'm giving you now as the final product. This is just educational, and it's for you to understand how it's produced. I'm not going to go through, no, I won't go through this example because we are running out of time. So by the end of this project, I want you to understand what cash flows are. And that's what this is about, actually. You can read this yourself afterwards. I want to talk to you about construction expenses, contract obligations, operating expenses, revenue. How do we calculate revenue from solar? That's in part 3 of it. We'll go through in a fair amount of detail how you calculate revenue from solar and wind. We'll talk about discounted cash flow analysis, which gives us our net present value, our project IRR. We'll talk about depreciation, we'll talk about debt, we'll talk about principal payments, annuity payments. You'll understand what equity is, you'll understand what CFADs are, debt service cover ratio. You'll understand the technical, well, put this way, it's better if you already know how to use Excel, but if you don't, we go through it in a fair amount of detail, how to use Excel. We'll talk about best practices in modeling, and we'll talk about much more as well, okay? One of the crucial things you'll be able to do is by the end of this course, you will be able to interpret and put inputs and get outputs from the Welsh Government Energy Service financial model, which is notorious for being a very difficult task for people to do. But I will show you how to use the Welsh Government Energy Service model. It's a model that's freely available to everybody. It's a very good, highly sophisticated project finance model. And if you can learn how to use it, that's your go-to. But in order to learn how to use it, do the course first, because otherwise it'd be very difficult. I'll end with this, the assessment. I am not a fan of assessments for assessment's sake. So I wanted to, and this pretty much sums it up. I want you to, at the end of this project, to write a report based on something like this. I'm going to give you a location of somewhere in Wales, or I can't remember where it is. I'm going to tell you that you want to build a 5 megawatt solar farm. I'm going to tell you which way it's facing. I'm going to tell you your plant availability. I'm going to tell you what your capex is. It's going to cost you 5 million. I'm going to tell you how much your grid connection is going to cost. I'll say to you, your OPEX is 15,000. That's your operating expenses. And you're going to sell this electricity for a whopping 11 pence per kilowatt, which is something you're never going to do in real life. I'll tell you that it's going to be done in a year. And I'm going to tell you that your project is going to take 25 years to actually operate. I'm going to ask you, does this project work? And by the time you're at the end of this course, you will tell me if this project can work or not. You will be able to say to me, Michael, how shall I fund this project? Shall I use, what sort of debt equity ratio shall I use? What depreciation schedule, what debt schedule can I use? Tell me if it makes a difference. You'll be able to answer all these questions, okay? You'll be able to say what your project IRR is, your net present value, your minimum debt service cover ratio, and your equity IRR. And from this, you'll be able to apply the rules, which you know, to say to me, okay, well, if a net present value is above 0, that's okay. If my IRR is above a certain hurdle rate, we're good. And if my debt service cover ratio is above 1.2, then we can proceed. And if that isn't the case, you'll be able to figure out why and understand finance modeling. Importantly, things we do not cover in this course, okay? We do not look at tax in great detail for good reason. We don't look at interest during construction. We don't look at P90, P50 figures and so on. We don't look at inflation and consumer price index. But look, at the end of this, right, you'll be able to do all of this. You'll be able to put in another month of research and you'll be able to answer all of these questions, because it's just a case of adding on more stuff to the model. It's easy enough to put inflation into the model. You'll be able to do it. We just don't do it here. We don't look at payback period. You'll be able to calculate that. We don't look at levelized cost of energy. We do actually look at levelized cost of energy at the end of Nathan's course, because I wrote that section. We don't look at dividends, decommissioning, debt service reserve account, maintenance reserve account, fees, development costs. We don't look at a lot of things. So that's a caveat. This is a basic course which will get you to a certain level, and then you have to do more then to get to the next level.